So our parameter in our null and alternative was always a p, a proportion. And just like we had seen in the previous chapters, when we had a proportion, we always converted it into a z-score, and then we could look up our probability. And if the probability is less than alpha, what does that mean? We reject it. Okay, if it's greater than alpha, we would fail to reject. When we're talking about the mean, so if you remember on the last test, if we're looking, I don't have a formula sheet, on your formula sheets, when we were doing like confidence intervals, if you look back under the confidence intervals for chapter 9, when we were doing a confidence interval for a proportion, we used that z value. But when we were doing a confidence interval for the mean, we didn't use z. What did we use? The t value. Remember that t distribution, that second table? So if we are talking about hypothesis testing around a mean, we are going to be using the t statistic to do that. So first, let's kind of refresh how to use that table. So if you look, oh, got a typo on that. So table number 7, our t distribution. Remember, it shows you the picture at the top. This table gives you area to the right, so it's the opposite of the normal. And to do it, we have to know the alpha level, which is the number across the top, and the degrees of freedom, which is the side. How did we get degrees of freedom? So this one would have 29 degrees of freedom. All right, so what it means, I didn't say you had to draw a picture, but I just want to illustrate it. We want area to the right. So essentially we're saying this area is 0.025, and we have to find the t that makes that happen. So if we look at our table, that picture matches the top perfectly, so we just go to row 29, column 0.025, and what is our t statistic?
2.045.
Is that okay? So, this one, a left-tailed test. So that means we want area to the left. So this is 0.01. We need the t. How many degrees of freedom do we have? Okay. With this distribution, we have to remember it is centered at 0. So my table is going to give me area to the right. How would I do the left t then? It's a negative of the t in the table. So we go to 6 degrees of freedom over to 0.01, and that is 3.143. But because it's the left side, we know it would be a negative. C, a two-tailed test with n equals 24, so that means there's 23 degrees of freedom. What do I mean by two-tailed? Both sides. Okay. So I need 2 t values. Okay, when I'm looking at these, the total area in those tails is 0.01, so how do I find out how much is in each? So this would be 0.05 on each one. So we go to 0.05, 23 degrees of freedom, and that's 1.714. So that would be this t. What would this one be? Negative. So I'm just going to put plus or minus. So two-tailed, we have both options. Any questions, sir? So let's talk about the hypothesis testing. Just like when we're doing it with the population parameters, the P's, we have multiple options. We can do the classical approach, we can do the p-value approach, and we can also use our calculator. I'm going to show you all of them. I don't use the classical approach very often. If it makes sense to you, great, you can use it. I tend to use the calculator more on these, just because our t-distribution, we are very limited here. We only have certain probabilities across the top. We only have certain degrees of freedom. So using the table on this, especially if you have a bigger sample, it's not very accurate. So for the most part, I do these on a calculator, but we'll talk through how to do them by hand as well. So our approach, we have, of course, our criteria. Has to be simple random sampling, no outliers, normally distributed, or at least 30, and the samples are independent. When I'm looking at these and I want you to check criteria, you need to check, is it normal or n greater than or equal to 30? That's what we are always doing. Before, in the previous chapter, we had criteria for P and we had criteria for X bar. And anytime we talked about X bar, we either had to say it was normal or that our sample was bigger than 30. So that's really the only criteria I'm going to ask you to verify. Most of the problems aren't going to give you enough information to know if it was a true simple random sample, and they're all independent. So we're kind of assuming that part. Then we have to set up the null and alternative hypothesis, which is just the same as the last one, except our parameter is the mean, mu. The alpha level will be given in our problem. The classical approach is you find your t-value, which is kind of like finding your z-score. So it's your value minus the mean divided by standard deviation. And that formula is on your formula sheet, just like every other formula. If you look at the top, chapter 10, it tells you the t-value formula, so we can have that right there. Then in the classical approach, you find your t-value, and if it is in the shaded region, depending on if it's less than, greater than, or two-tailed, you would reject. And if it's not in that shaded region, you fail to reject. If we did the p-value approach, we go ahead and then find our p-value from the table or from a calculator, since that's more accurate. And then if the probability is less than alpha, we reject, which is how we did most of the problems in the last section. So let's look at a problem. I'm going to do this one by the classical approach just to show you that, and then I'll probably do mostly the p-value approach. So I want to test my null hypothesis. The mean equals 80. The alternative, the mean is less than 80. We have a simple random sample of size 22 obtained from a population that is normally distributed. So my sample isn't big enough to assume normal, but I told you it was normal. So my criteria is met. I want to find my test statistics, so I'm looking for my t-value. So our t is, if you're looking at your formula sheet, everybody find that under chapter 10, X bar, so the mean of our sample, minus mu, the mean in the null hypothesis, divided by S over the square root of n. Make sure you do parentheses around the numerator and the denominator in this. So my t is negative 1.711. Alright, now we have to find our critical value from the table. So how many degrees of freedom do we have here? We are testing less than. So less than is down here. My alpha level was 0.02. So we need to find this t value that matches it. So we go to our table, 0.02, 21 degrees of freedom. And then how do I show that it's to the left? Negative. So t equals negative 2.189. So our third step, I'm asking for a picture, which I already kind of drew. But what that's saying is, here's our critical value. If we do the classical approach, then anything in this shaded region we would reject. When we found our test statistic, we got negative 1.711. Remember, this is centered at 0. So is negative 1.711 in this shaded area? No, because it's centered at 0. So negative 1.7 would be like here. So our conclusion, since our t statistic is not in the shaded region, we fail to reject. Okay, we don't have enough evidence to prove that the mean is lower than 80. So that's our classical approach. Any questions on that one? So let's talk through using a different approach. So assume the resting metabolic rate, RMR, of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found the mean RMR to be 5,708.07, the standard deviation of 992.05. At the alpha equals 0.05 level of significance, is there evidence to conclude the mean RMR of males listening to calm classical music is different than 5,710? All right, we're talking about a mean. Anytime I'm talking about my mean, what's my criteria? It's either has to be, tell us it's normal, or it has to be bigger than 30. Is my n greater than 30? All right, so we're good there. Then we need our hypothesis. We're talking about the mean, so that's mu. What is my null hypothesis? The alternative. Right, we want to know if it's different. So that's not equal to. Everybody okay so far? All right. Just kind of a note over here. What is my alpha level? How many degrees of freedom do we have? All right. So now we need to find our t statistic. So that's x bar. The mean of our sample was 'This is our x bar, the mean of our sample. So it's x bar minus mu, that's the null hypothesis mean, divided by S, which was divided by the square root of n, which is 45. -0.013. Everybody with me so far? So now we need to compare it to the critical value. So we are testing not equal. That means it's a two-tailed test. If my alpha is 0.05, then how much goes in each tail?
0.025.
Okay, so now we need the t from the table. So we need 0.025 and 44 degrees of freedom. Do you notice a problem? We don't have 44. So what's the closest our table can give us? 40. So if I'm going to do it by hand, we have to stick with 40, but we already know it's not perfect. Because it's two-tailed, it's the plus and the minus. So this is like a negative 2.021. This is a positive 2.02. Okay. So is our t in that shaded region? No. So would we reject? No. Let's talk about how to do this on the calculator as well. I think I did give you guys an empty box here, so hopefully you've got enough room to kind of write it down. Yes.
What did you get to 2.02?
On our table,
Oh,
44 degrees of freedom and 0.025. Okay, so on the calculator, you go into stat, tests. Okay, remember when we did confidence intervals around the mean? We did a t interval. So if we're doing hypothesis tests around the mean, we just want a t test. So it's number 2. So stat, tests, number 2. Okay, then it asks us some questions. Do we have data or statistics? Data would be if you put values in L1. We don't have that, so we have statistics. Okay, the mean of the null hypothesis. What was that? Okay, the x bar, the mean of our sample. Standard deviation of our sample. Okay. Our number. We are testing not equal to. And then calculate. What I would like, when you do these on the calculator, it's really hard to show much work. But I would appreciate if you do your problem on the calculator. You obviously have to write down the null and alternative hypothesis at the beginning. Then it would be nice if you wrote down your t. Is that the same t statistic we did by hand? and then our probability. Okay, if we're doing this approach, we reject if P is less than alpha. Is our probability less than alpha in this problem? No, nowhere close. So since P is greater than alpha, we fail to reject. So that is the p-value approach, just finding the probability. And you only reject if it's less than alpha. Questions there? Let's look at this one. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. So we have 18 state quarters. He weighs them and gets this data. So, what is my null hypothesis? Mean is 5.67. What's the alternative? Okay, my criteria, we kind of have a problem, don't we? Do I have a big enough sample? No. Did it tell me that it was normally distributed? No. That's kind of my mistake. I really meant to include that in the problem. So let's just add into our problem. Assume it's normal. I accidentally left that part out. And we have to be given that it's normal because our sample isn't big enough otherwise. Okay. What am I going to do next? Yeah. So we need to go to stat, edit, and we need to put all of this in L1. Let's go ahead and do this on our calculator. So if we wanted to go to stat, tests, which test do we do? T-test, number 2. Am I basing it off data or stats? Okay, the mean of the null, 5.67. The list is L1, frequency is 1, we're testing not equal to. So we calculate. So then we have the T is 2.753. And the probability is 0.136. All right, so what does that mean? Reject or fail to reject?
Reject.
Right. Why?
Because it's smaller than
Since P is less than alpha, we reject the null hypothesis. There is evidence to conclude that the state quarters have a different mean.
So we only reject the probability if P is greater than alpha?
You reject when P is less than alpha.
Okay.
What if we put the frequency?
So frequency would be like if instead of giving you all the data, I made a table and I said I got 5.7 4 times and I got this 3 times, and then you could do frequencies like that. What if I wanted to do this one by hand? we're still a little bit limited because I just gave you the data, right? So we would need a few things from our calculator. How would I get the mean from my calculator? Stat, calc, one variable statistics, remember doing that? Oh. So your list should be L1, frequency list should be blank. So if I did that, then we know the X bar. We know the standard deviation. What's wrong?
I don't know, mine's like weird. It doesn't have anything filled in my list.
So then we would have to find our T statistic by hand. So that's our mean minus the mean of the null hypothesis, which was 5.67, divided by S, divided by the square root of N. So we get 2.749 for the T statistic. So then if we're doing the classical approach, we know the alpha was 0.05. How many degrees of freedom? Since we're testing not equal, right, that's a two-tailed. So we know you have to take the 0.05 divided by 2, so it'd be 0.025 on each tail. So you'd have to go to your table and look up 0.025, 17 degrees of freedom. And we get plus or minus 2.11, I lost 0. Okay, is our T in the shaded region? Yes, 2.7 would be over here. It's in the shaded region. And so that means we reject. So we can do it either way. If you're doing the probabilities, easiest to get those on the calculator. If you're just looking at your critical value, you can do that by hand. Any questions? Okay, I want you guys, just ignore the next slide for a minute. I want you to set up this last example. See if you can work it out. You can do it on the calculator. You need to write your null and alternative hypothesis. I want your T. I want your probability. What criteria do we have to verify? And how big was our N? Okay, so we're good there. The null hypothesis. Okay, so it told us that when it started, the mean was 25.2. The alternative. I want to test if the mean has increased. So the alternative would be greater than. You guys okay there? Alright, if we're going to do this on the calculator, you have to input some things. So we'll have to know our X bar. What is our sample mean?
25.5.
We'll have to know our S. We'll have to know our N. Okay, so if we go stat tests number 2. This time we're basing it off stats. I don't have the 1200 results. I have this data. The mean of the null by 5.2. X bar 25.5. Standard deviation, 4.8. My N is 1200. We are testing greater than. So calculate. So my T is 2.165. Probability 0.015. So what's my conclusion? Since the P is less than alpha, which was 0.05, reject the null hypothesis. There is evidence to conclude the mean age has increased. Okay, this is an example of something that statistically we found a difference, but practically does it really matter? If you're talking about the mean age, is there a big difference between 25.2 and 25.5? No, we're talking about the average is a couple months older than what it was before. So while we found a difference, it's not what we would necessarily consider practically significant. So if you ever hear that term, just means that while there is a difference, it really doesn't matter. Okay, there's not enough of a difference to really matter. In this scenario, it doesn't really matter if you're a couple months older. You're still 25 years old, so it's essentially the same. All right, any questions for me? So we're done with chapter 10. We have the handout we've been working on. I'm planning tomorrow to just give you time to work in class. If we need to do a little bit of review, we can. But I really just wanted tomorrow to be time to work on this handout because I know I've taught for most of the class today. Then Thursday, I will probably give you another chapter 10 handout just with all of it mixed together. So instead of having it broken down into sections where you're doing the same thing on all the problems, I'll have them mixed together. Friday, I'm going to be gone for a conference, so I would like to do a quiz Friday of the chapter 10. But that's what we will be reviewing on Thursday and tomorrow. Is that okay?